we shall discuss after discussing the models and their solution. In the previous lecture, we were discussing a string. If we have a string attached to a rigid kind of support, and the string was basically just like this. Okay, this was the string, and a mass. We assume that a mass is attached to this spring. And obviously, there is some extension in the spring if we attach a mass to the spring. So there must be original length of the spring and some kind of elongation or extension in the spring. And that extension was S. You can see the previous lecture for more details. Now, if we pull this mass downward and leave it, then this mass will start moving. Definitely, it will have a to and fro motion or simple harmonic motion. And the differential equation we derived in order to describe this to and fro motion was basically d square x by dt square plus m times dx square by dt square plus k times x is equal to 0, subject to the conditions x of 0 is equal to x naught and x dash of 0 is equal to some x1. This was the model we derived in the previous lecture. In fact, we assume that there is no other force acting on this spring. Only there is no frictional force. We assume that the spring mass system is in vacuum because there are no frictional forces applying on it. There were only two forces: the weight force W and the restoring force, which we assume that it is Fs. The weight force is obviously mg, and the restoring force was k times s. And it is always negative force because it is acting opposite to the basically motion of this mass. So this was the model which we derived in this situation. We can, if we analyze the initial conditions, for example, this one, x of 0 is equal to x naught and x dash of 0 is equal to x1. So this is initial condition on the displacement of this mass, because x of t is basically, it describes x of t basically represents the position of mass which is moving at any time t. So this initial condition is basically on the displacement of the mass, and this is basically the velocity of the mass. Now there are some special cases when we discuss such kind of systems. For example, the case one is on the initial conditions. If x naught is greater than 0, means the displacement is positive. We pull down this mass, then there must be some displacement in the position of this mass. So the spring will be extended even more. And x1 is less than 0. If this is the case, it means that we pull down the mass and we leave it with an upward velocity, with an upward negative velocity, okay, of x1 units. Okay. What does this mean? The mass is pulled down, mass pulled down x naught units, and that mass is left with an imparted velocity mass is left with an imparted upward velocity x1. This is what we mean here by the initial conditions. Now, case 2, if in a case 2, if x0 is less than 0 and x1 is greater than 0, what does this mean? It means that the mass is pulled upward or pressed upward. Okay? The spring will be pressed. Okay? Then the displacement will be negative from the equilibrium position. Again, यहाँ पे, if we pull it down, there will be displacement, which we call that initial displacement x0. This will be greater than 0. And when we press this spring, the mass is displayed upward, there will be a negative displacement from the equilibrium position. And when we pull down it and leave with the velocity x1, it will be upward velocity, okay? And that velocity will be negative always. And if x0 is 0, then the mass is pulled upward, and then we leave it with an imparted velocity which is downward, and we consider it positive. So mass pulled upward x0 units. Okay. x0 units, definitely this x0 will be negative. And the second thing is mass is left with an imparted downward velocity x1. Okay, so this is what you have to remember here. In the third case, if x0, for example, is greater than 0, and you can take it only for x dash of 0 is equal to 0. If this is 0, if the velocity is 0, what does it mean? The mass is either pulled down or upward and left with the initial velocity 0. Okay. Means it is left from the rest. So this is what you have to remember for solving spring mass system problems. For example, we have, okay, let me discuss the model again. M d square x by dt square, we can write this equation in this form, divide throughout on both sides with m, and we obtain d square x by dt square plus k divided by m, x is equal to 0. Now we assume that this k by m is equal to omega square x is equal to 0. Sorry, omega square is equal to, where omega square is equal to k by m. Now this is a second order ODE, and it is homogeneous and it has constant coefficients. We can solve this ODE easily by writing its characteristic equation. We can write this equation in the form d square plus omega square times x is equal to 0, and the characteristic equation will be what? It will be m square plus omega square is equal to 0. Now, how can we find the roots of this equation? We need to find its roots. If we have an equation of this kind, we can write it m square is equal to negative omega square, and definitely m will be plus minus omega into iota, because here we have a negative sign. So these are basically complex conjugate roots. If we have complex conjugate roots of a characteristic equation, then how can we write basically the general solution? Here we can assume that there is 0. In this case, the solution of that equation will be what? E raised power 0t times c1 cosine of omega t plus c2 sine of omega t. So this will be the solution of that spring mass system. Is basically free undamped motion. C1 cosine of omega t plus C2 sine of omega t. So this will be the solution of that free undamped motion, where C1 and C2 are basically two constants of integration, which can be computed by using initial conditions, and the initial conditions are x of 0 is equal to x1, sorry, x naught, and x dash of 0 is equal to x1. So this is how we solve the free undamped motion equation. Okay. If you have any question, you can ask me. Now let us discuss an example of this kind of model. Example is given here. There's a question in the chat window that can you explain how we moved from d squared to m squared in the characteristic equation? We did not move, basically, we wrote the characteristic equation corresponding to this differential equation. It is basically a differential equation where d squared is what? D squared is d squared by dt squared. We just changed the notation of this differential equation just to know how to write the characteristic equation. Characteristic equation is basically what? It is nothing but you just replace d by m. We discussed these things in the previous lectures. I hope you know it. No, it is not a mass. It is basically, we divided that mass on both sides. This m, we divided it here, okay, and we obtain this now. We assume that this is omega square. We assume it just to basically simplify the calculations, okay. Because if we put here only omega, we would have roots as here square root of omega times iota, and we have to put here square root everywhere. So just to avoid the square root in the calculations, we assume that it is omega square. And this omega is called angular frequency. Angular frequency of that free undamped motion. And what is the frequency of, I explained in my notes what is the angular frequency. Omega is what? Omega square is, if it is k by m, then omega is square root of k divided by m. And it is called angular frequency. Frequency of that free undamped motion. What is period of the motion? There are certain things you need to know. Period of the motion is what? It is denoted by t, and it is 2 pi by omega, where omega is what? Omega is this thing. And what is this period of motion? Period of motion is the time in which that mass completes one cycle of the motion. Okay, this is period of the motion, and there is one other thing which we discuss in these kind of systems. spring mass system, frequency of the motion. Frequency of motion. Frequency of motion, which is called basically the natural frequency. Natural frequency is, it is F, denoted by F, and it is 1 over T. 1 over T, where T is what? It is the period of motion. Frequency, what does this frequency describes us? It is basically how many cycles of that motion of mass have been completed in 1 second. This time is basically usually described in seconds, and the period of the motion is what? It is the time in which one complete cycle of that motion of that mass has been completed. This is the period of the motion. And how can we calculate it? We have to solve that problem. After solving, we get this solution, and here the coefficient of t, it is here, it is in the angle of cosine. We can compute the omega from here. If we know the omega, we can compute the period of motion by just dividing it here, 2 pi by omega. And frequency of the motion, it is F, denoted by F, and it is 1 over T. It is the reciprocal of the time period. I hope you know it. All these things have been explained in my notes. You can read them for more details. Now let us discuss an example of this thing. A mass weighing 2 pounds, change the board. Example, mass weighing 2 pounds, means weight of the mass is 2 pounds. Pounds is 2 lb in short. Okay. A mass weighing 2 pounds stretches a spring 6 inches. So if we attach a mass, यहाँ पे I made with that spring, 2 pounds of mass have been attached, okay? And the spring the mass stretches that spring 6 inches. Means the stretch is what? Stretch is, it is denoted by, usually by basically S, and it is 6 inches. Okay, 6 inches, or you can say 1/2 feet. At time t is equal to 0, the mass is released from a point 8 inches below the equilibrium position. It means 8 inches below from the equilibrium position. It means x of 0 is equal to 8 inches. I explained you what is this thing. X naught, when the mass is attached to a spring and you stretch it down, or you attach a mass of 2 pounds, then the spring will be stretched from the equilibrium position. So it will give us x of 0 is equal to 8 inches. Or you can say 8/12 feet, and it is 4 2s are 4 3s are 4 2/3 feet. Within at time t is equal to 0, the mass is released from a point 8 inches below the equilibrium position with an upward velocity. With an upward velocity 4/3 feet per second. Upward velocity means x dash of 0 is equal to 4/3 feet per second. If it is upward velocity, as I explained you earlier, how to interpret the initial conditions in the problem, when you leave a mass by pulling it down with an upward imparted velocity, then it will definitely be negative always. determine the equation of motion. So we have to find the equation of motion, and the given data is this. Okay. So what is the data? We have a spring attached, attached to a basically a support, and with that spring we attach a mass of 2 pounds, and that stretches the spring downward. Okay. Then the stretch in the spring is what? It is 6 inches, and we leave that mass, or the mass started moving below the equilibrium position. And how much below? It is 8 inches below the equilibrium position. Then x of 0 is equal to 8 with an imparted upward velocity 4/3 feet per second. If the velocity is upward, then it will be always negative here. So this is our data. We have to construct a differential equation which describes this free undamped motion. As there are no other forces applied on that spring, so it is basically the free undamped motion. Ab dekhiye, at time t is equal to 0, the mass is left from the equilibrium position. So if the position, if that system is in equilibrium position, then W is equal to Fs. W is what? It is the weight force. Fs is what? It is the restoring force. W is equal to what? W is equal to mg, and we have given weight. We can have this 2, we can have m. We need to find the m in order to construct that differential equation, because the differential equation is what? It is m times d square x by dt square plus k times x is equal to 0. So we need to find m and we need to find k here. So here in a British units, SI units, they take g is equal to 32, because in this book, which we are basically considering as a recommended book, which we have uploaded, and I have picked this example from that book of Dennis Giesel. They are using British SI system of units. So in British SI system of units, g is taken as 32 meter per second square, because it's a gravitational acceleration. And if we solve it, we can obtain m is equal to 1/16 slugs. It is again the British SI unit of mass. Okay, we have to consider this thing. Now, by using this law, we can compute m, and now by using F as restoring force, we know that it is always k times s. Okay, so we have, and Fs is equal to W. So W is equal to k times s. W is 2, k is k, and s is what? It is 2/3 feet. Okay. 2/3 feet? No, 1/2 feet. It is 1/2 feet. So it is 1/2 feet, and k is what? K is 4. By using this restoring force and the equilibrium position, we can compute the value of k. Now, inserting the value of m and k here, m is what? M is equal to 1/16, okay, and it is d square x by dt square plus k. K is what? It is 4. 4 times x is equal to 0, along with, or subject to these initial conditions, which are x of 0 is equal to 2/3, and x dash of 0 is equal to -4/3. So this is the model which represents this motion. I hope you get it. If you have any question, you can ask me. There's a question in the chat window. No, these are old questions. So the question was, I'm gonna repeat it. A mass weighing 2 pounds stretches a spring 6 inches. At time t is equal to 0, the mass is released from a point 8 inches below the equilibrium position with an upward velocity of 4/3 feet per second. Determine the equation of motion. So the mass has 2 pounds weight, it stretches 6 inches, and the mass is released at time t is equal to 0 from the point 8 inches below the equilibrium position with an upward velocity, upward impacted velocity of 4/3 feet per second. So this is what we obtain as a model. Now this thing, which we can solve very easily because this differential equation is homogeneous, linear, second order differential equation with constant coefficients. I hope you can solve it and get the solution. If you have any question, you can ask me. There are certain other examples given in my notes. You can see them and try to solve those examples for your practice. If you have any question, you can ask me. Otherwise, I'm going to discuss the next thing, which is free damped motion. Now we are going to discuss, first we have discussed free undamped motion, and now we are going to discuss free damped motion. Okay. Damped motion. And what is this? Now assume that this mass is experiencing, it is basically having some force acting on this, which slow down its motion. In free damped motion, we assume that this mass is experiencing some force which is acting on it, which slow downs its motion. It restricts to this mass to move freely upward and downward. For example, we can assume that an air resistance, if the surface of the mass is very wide, then there must be air resistance force which will definitely try to stop this mass from moving upward and downward. Okay, and that force is obviously the frictional force. Or we can assume that this is one example of the force which can act on this mass to slow down its motion. This basic phenomena is called basically a damped motion, free damped motion, because some force is trying to slow down the motion, and that kind of force is called damping force. Okay, the one example of that damping force is air friction. The second, for example, damping forces, you can consider damping forces as, number one, damping forces are those forces which basically apply force on this mass and try to slow down its motion. The example of damping forces are frictional force or air resistance, you can say. Air resistance. The second, that mass is immersed into some medium, for example, water. Assume that this mass is immersed in some medium. For example, this mass, if this is a mass attached to that spring, and this mass is immersed into water. Here, there's a container here which contains the water or some other kind of medium, and that mass is immersed in that medium. When we pull down the mass and leave it for the motion, then the surrounding medium will definitely impose a force which will restrict the motion of this mass, okay, which will try to slow down the motion of this mass. Now the motion of mass is damped. I hope you get it. If you have any question, you can ask me. Okay. Number 3, the third kind of the motion is damping force. Is basically we attach that mass to a mass is attached. You can say mass is attached to a dashpot. Dashpot, what is dashpot? Dashpot is a device. Basically, you can say that let me clean this board. If we have a mass here attached to a spring, then a dashpot is a device which basically you can say that which try to impose some force on this mass to move freely upward and downward. So dashpot is a device which basically imposes force, frictional force, or you can say that damping force on the mass to move freely upward and downward. Okay. It will definitely slow down the motion of the mass. You can see the picture of dashpot on Google as well. You can just type the dashpot. You can have the picture of the dashpot in Google. So these are basically a few damping forces which can be applied on the spring mass system, which will try to slow down the motion of that mass. And all these forces, damping forces, are basically, we can denote them by FC, and they are always proportional to the velocity of the mass. All these damping forces are basically proportional to the velocity of the mass, and if we remove this sign of proportionality, we can put a constant beta dx by dt. Then this beta is basically a constant of proportionality, and all these forces are basically against the motion of the mass. So definitely this force will always be a negative force, because the damping forces, they try to slow down the motion of the mass. So they are obviously act on the opposite direction of the motion. So there'll be negative forces, these damping forces. Now, if we assume this system free damped motion, then the equation of the motion, then this equation of motion will be basically will become, here we will have another damping force, which is negative beta dx by dt. Okay? Then the equation of motion will be changed to this equation, and after taking this thing on the other side, we can obtain the equation of motion equal to md square by dt square plus beta dx by dt plus k times x is equal to 0, subject to the similar initial condition x of 0 is equal to x naught and x dash of 0 is equal to x1. So this equation or this model basically describes the free damped motion. So this equation describes free damped motion. Only three forces are acting on this spring mass system. And these three forces are what? If we have a spring and a mass is attached to this spring, then there is a restoring force, Fs, there's a weight force, W, and there is another force which is basically a damping force. A damping force is always applied opposite to the motion of the mass, and it is Fc. Now there are three forces acting on this spring mass system. One is weight, restoring force, and the damping force. Now the equation of motion obviously would become here. And how can we express these three forces? It's basically what W must be equal to Fs plus Fc. Okay. Now we know that W is what? The total force. The total force on this spring mass system will be W plus Fs plus Fc. This will be the correct by using the Newton's second law of motion. Okay. So after inserting the values of W, Fs, Fc, we obtain this equation. For the explanation of these forces, you can see my previous lecture as well. I have explained how to derive this equation by using the Newton's second law of motion. So we obtain this equation, which is a second order homogeneous linear differential equation with constant coefficients. Mass is constant, beta is constant, and k is constant. Okay. After finding these constants in a particular problem, we can solve this differential equation by using the method of undetermined coefficients. I hope you know that. We have already discussed it. If you have any question, you can ask me. For example, let's discuss, so before discussing an example, let's discuss how to solve this kind of equation. In order to solve this differential equation, what we do, we try to simplify this equation. We divide this equation by m on both sides, and what do we obtain? D square by dt square plus beta by m dx by dt plus k by m x is equal to 0. Now, in order to simplify our calculations, we assume that let beta by m is equal to 2 lambda and k by m is, we assumed already, it is omega square, just to simplify our calculations. Okay. Now, let me go to what we have obtained here now. An equation of this form, dx square by dt square plus 2 lambda dx by dt plus omega square x is equal to 0. So this is the equation now which we have to solve we can write the characteristic equation easily as m square plus 2 lambda m plus omega square equal to 0. This is the characteristic equation, and we can find the roots of this equation easily by using the quadratic formula. M is equal to negative b plus minus square root of 4 lambda square minus 4ac divided by 2a. Now, here we have 4 and 4 here. Now, I hope you understand why we have assumed here that beta by m is 2 lambda. We put here 2 so that we can simplify this expression. We can take 4 outside and we can simplify with this thing, and we obtain lambda plus minus square root of lambda square minus omega square. So these are the roots of that equation. If these are the roots, we can easily write the general solution, which depends on the value of this radical. Okay. Lambda square minus omega square. Then there will be 3 cases. The case 1 here, because the general solution depends on the value of this this expression. In this thing, if lambda square is greater than omega square, then there will be real and distinct roots. Okay, real and distinct roots. When we have real and distinct roots, we can write the general solution as x of t is equal to e raised power minus lambda t times c1 cosine of, sorry, not cosine of, c1 e raised power negative lambda plus under root lambda square minus omega square times t plus c2 e raised power negative lambda negative under root lambda square minus omega square times t. So this will be the general solution because the roots are real and distinct. In case 2, okay, let me add it in this thing. When the lambda square is greater than omega square, then this motion is called overdamped motion. Overdamped motion. Overdamped motion means the frictional force will be more than other forces, restoring forces, weight force, as compared to other forces. The damping force will be a lot more greater than the other forces, and the mass, the motion of the mass will be opposed greatly, and the motion it will basically come to the its motion will be stopped, you can say, very quickly, because the damping force is much more than the other forces. This kind of system is called basically overdamped motion. Okay. The case 2 is when lambda square is equal to omega square, then this factor will be 0 and the roots will be real and repeated. In that case, when the roots will be real and repeated, we'll have this factor 0 and we'll have only minus lambda as a root. In that case, the solution will be c1 plus c2 t e raised power minus lambda t. So this will be your solution. In this case, we call that this free damped motion spring mass system is basically critically damped motion. Okay, critically damped motion, that the damping force is almost equal to the restoring and weight force, and the motion will stop after a certain time. Okay? It will take more time to stop that mass than this case, because this is an overdamped motion. In this case, the mass will be stopped very quickly. The third case is when the lambda square is less than omega square. The lambda square is less than omega square. Case 3, it is called underdamped motion. Underdamped motion. Underdamped motion, in this case, lambda square is less than omega square, and we obtain complex roots, complex conjugate roots. And in that case, the roots will be minus lambda plus minus. Lambda square is less than this, we can write it omega square minus lambda square times iota, okay, where this thing is now greater than 0. In that case, the general solution will be x of t e raised power minus lambda t times c1 cosine of omega square minus lambda square t plus c2 sine of omega square minus lambda square t. So this will be your general solution in third case. Now, if you have any question, you can ask me. There's a question in the chat window. Was overdamped motion in case 1 or case 2? Case 2 is critically damped motion. Case 1 is overdamped motion. Okay? Case 1 is overdamped motion, and case 2 is critically damped motion. Critically damped motion. Overdamped motion means damping forces are much more than other forces, and they will stop the motion of mass immediately. Okay. Critically damped motion means the damping force is somewhat, you can say, equal to the restoring and weight force, and it will take more time to stop the motion of the mass. Underdamped motion, in this case, the this damping force is lot more, you can say, less than the other forces, and it will impose a very less force, okay, a low amount of force on the mass to stop its motion. Okay, so in this case, the motion of the mass will be stopped after a long time. Okay, so this is called underdamped motion. Okay, because in this case, the amount of force is very low as compared to other forces. So this is called underdamped motion. Okay, I hope you get it. If you have any question, you can ask me. Now let's do an example of this thing, and we will discuss further things after this example. Now this is the question now. Example, let me clean the board. So let's discuss this example of a 4-foot spring measures 8 feet long after a mass weighing 8 pounds is attached to it. Means we have a spring, its length is 4 feet, and when we attach a mass to it, its length has been extended to 8 feet. The medium through which the mass moves offers a damping force equal to square root of 2 times the instantaneous velocity. There's a medium in which the mass is immersed, or you can say submerged into that medium, which I told you the second kind of force. You can say we have a contact Okay, there is a medium here, for example, the water or some other kind of thing, and the mass is submerged here, M here, and the spring is basically, and it is attached to a spring, this way. So there is a container here which has a medium, and the mass is submerged into that medium. So this medium will definitely impose a force, damping force, which will try to stop the motion of this mass. Okay, and it is what the medium through which the mass moves offers a damping force equal to square root 2 times instantaneous velocity of the mass. So instantaneous velocity is what? It is dx by dt, and it is square root 2 times instantaneous velocity. It is the damping force. So it is your damping force, and it will be definitely a negative force. Now, what we have to do, find the equation of motion if the mass is initially, find the equation of motion if the mass is initially released from equilibrium position with a downward velocity of 5 feet per second. The mass is released from the equilibrium position. What does it mean? It means that x of 0 is equal to 0 with a downward velocity of 5 feet. Velocity is this, x dash of this is 5 feet per second. Okay? And it is the downward velocity, so we'll have a positive here, positive sign here. In the case of upward velocity, we have a negative sign. In the case of downward velocity, we have a positive sign here. Okay? Now we have to find the time at which the mass attains its extreme displacement from the equilibrium position, and furthermore, we have to find what is the position of mass at this instant. So this is the data we are given. The spring length is, originally it is 4 feet. When we attach a mass to it, its length becomes 8 feet. So the basically extension or the stretch in the spring is what? Stretch is basically S, and it is what? It is 4 feet. Because the original length is 4 feet. After attaching the mass, it becomes 8 feet. So there will be extension or stretch of 4 feet in that string. With the mass, the mass is what? M. It is 8 pounds. Okay. Weighing, so it's weight, it's not mass. A mass of whose weight is 8 lb, 8 pounds, so its weight is, W is 8 pounds, not mass. Because it's given in pounds, so it must be weight, and the mass, the unit of mass is slugs. So how can we construct an equation of motion which describes the motion of this phenomena of string mass system? We know the equation in this case is what? M d square x by dt square plus beta times dx by dt plus k times x is equal to 0. Now you can find the value of m from this equation, because weight is what? It is mg, and g, the value of g is what? 32. So we can find from here m is 8 by 32 plus. 8 by 32 means 1 by 4. It is 1 by 4. And from here, we can find, as we leave the mass from the equilibrium position. So in equilibrium position, W is equal to Fs, and W is what? W is 8. Fs is K times S, 8Ks. S is what? It is 4 feet. So we have 8 is equal to 4 times K, and the value of K is 2. So we obtain all the things here The mass is what? 1 over 4 d square x by dt square plus beta x by dt is what? Beta is what? It is square root of 2. So we'll have square root of 2 here, dx by dt plus k. What is the value of k? It is 2 times x is equal to 0. So this is our differential equation which describes this motion along with the initial condition x of 0 is equal to 0 and x dash of 0 is equal to 5. So this is the model which we are going to solve here in order to describe this phenomenon, this spring mass system. I hope you can solve this differential equation along with the initial conditions and find the solution. And in order to find the maximum displacement, you can use the calculus 1 technique. How to find the maxima of any function. I hope you know it. Can anyone tell me how to find the maxima of a function? You have already studied this in Math 101, Calculus 1 course. You find the derivative of that function and put it equal to 0, find the points and check where the maximum position is this. All these things have been solved in my notes. You can see things there if you have any problem. There's an application of pre-damped motions. Let's discussing force now. What we have discussed now, we have discussed pre-damped motion. Now we are going to discuss forced damped motion. Forced damped motion. Again, in a spring mass system. In the previous topics, what we have discussed, free undamped motion. There are no other forces except the restoring and weight force. And then free damped motion. In that case, we had an additional force, which is basically damping force applying on the motion of the mass. Now we are going to discuss forced damped motion. Again, if we are given a spring, okay, and a mass is attached to this spring, okay, and there are 3 forces: S, restoring force, the weight force, and again another force which is damping force applying on this spring mass system. Okay, these are 3 forces applying on this spring mass system. Now, if there is another force which is being imposed externally, which helps the mass to move, okay, or which helps the mass to increase its motion, okay, and that force, external force, we call it basically external force, okay, and you can call it Fe maybe, okay. An external force is basically applied on this whole system to increase the motion of this mass, which helps this mass to basically move in to and fro motion, or you can say the simple harmonic motion. And in the equation, this force could be basically, if this is an external force, then we can say that this force is added here in the equation because it's an external force. And this force is basically applied on the whole system. For example, the forces applied, this support where the spring is attached, this support starts moving. Okay, this is not a rigid kind of support. If this support starts moving up and down, then it will definitely impose an additional force on this mass, which will definitely help this mass to move upward and downward. Then this kind of force is basically called an external force, and this kind of system is basically called force damped motion. Usually, how do we move this support upward and downward to impose the motion? And that motion is also a kind of simple harmonic motion, or you can say a periodic motion, which is being imposed on the support of this whole spring mass system. Usually this force F of t is some constant times cosine of some, you can say constant, यहाँ पे आप gamma t कर दें. This could be cosine of some constant times cosine of some constant times t, or you can say some constant times sine of gamma t. Okay? Because that support is now moving upward and downward, or it obeys basically the periodic motion. So the periodic motion is best described by these kind of functions. So this force is in a spring mass system, we consider it always of this form. If we add this force to this spring mass system, then the equation will become this thing, along with the same initial kind of conditions, x of 0 is equal to x naught and x dash of 0 is equal to x1. So this model, mathematical model, describes force damped motion for a spring mass system. I hope you get it. If you have any question, you can ask me. Let's discuss an example of this thing, then you will understand it. Forced oscillation भी कह सकते हैं आप इसको. Force damped motion, because you are forcing the oscillations of the mass to impose a force on the support where the spring has been attached. An example of this thing is basically what? Example of force damped motion. Or you can say forced oscillation. A mass of one slug. Now, a mass of one slug means it is m, not w, because now the mass is given. A mass of one slug stretches a spring 2 feet and comes to rest at equilibrium. Okay. What does this say here? A mass of one slug stretches the spring, stretches what? Stretches 2 feet. A mass of one slug, when it is attached to a spring, it stretches that spring 2 feet and comes to rest at equilibrium position. The system is attached to a dashpot that imparts a damping force equal to 8 times the instantaneous velocity. This system is attached to a dashpot, which imposes basically damping force. Damping force is equal to what? It is equal to, damping force is equal to 8 times instantaneous velocity of the mass. So it is 8 times dx by dt. Now, next, find the equation of motion if an external force equal to, if an external force Fe is what? External force is applied on the whole system, which is equal to 8 sine 4t. So this is your external force is applied to the system beginning at t is equal to 0. Now we have to construct a differential equation which describes this motion. There is a question in this chat window. Should we take, what is the question? Should we take damping force as negative? Basically, damping force, but when it goes on the other side of the equation, when we use this Newton's second law of motion, it becomes positive. Okay, when we use m squared d square x by dt square plus beta dx by dt plus k times x equal to z equal to f of t now, because there is an external force. Because when we apply Newton's second law of motion, it is basically d square m square dx by dt square is equal to what? Equal to negative beta dx by dt and negative k times x. Because beta is negative, so we will have negative here. And restoring force is negative. We have, just a second. Beta is negative, so we have negative here. When this term goes on the other side, it becomes positive. Okay. Similarly, the restoring force is always negative, but when we take it on the other side, it becomes positive. So that's why you can basically say that it is negative, but when we put it on, so this one, you were asking for this one, not this one. When this is negative and we take it on the other side of the equation, on the left-hand side, it will definitely become positive. So you can put a negative sign here, but in the equation, you have to take it positive here. So what will be equation? M is given, S is given. S is given, okay. We have to compute the K. And if the system is in equilibrium position after attaching the mass, then W is equal to Fs. Okay, and W is equal to what? It is mg. And what is Fs? It is K times S. Okay. Now from here we can compute the value of K. Because M is what? It is 1. G is what? It is 32. And K is K, and S is what? It is 2. So what is the value of K? Value of K is 16. Okay. We have already the value of beta, and we have an external force. So the equation of motion will become here, this thing, it is not m square, it is m. M is 1 d square x by dt square. You cannot see it. Plus 8 times dx by dt plus what is the value of k? 16. 16 times x is equal to what? Is equal to 8 times sine 4t. So this will be your equation of the motion which describes this damped motion of that mass. Now, when the mass is in equilibrium position, definitely there will be no displacement, and there is, in the question, it is given that a mass m of one slug stretches a spring 2 feet and comes to a rest at equilibrium position. When the mass is at rest, then obviously its velocity will also be zero. So this is the mathematical model which we obtain for this spring mass system in this example. So you have to solve this differential equation, which is a non-homogeneous linear second order differential equation with constant coefficients. And we have already discussed how to solve these kind of differential equations. It is what? It is non-homogeneous because the right hand side is not zero here. Okay, we are going to solve this differential equation by using method of undetermined coefficients. Okay, we can find the particular solution, but first we have to find the complementary function of the associated homogeneous differential equation. We put this left hand side equal to 0 and we find the complementary function, and then we can find the particular solution, which depends definitely on the nature of the right hand side function. I hope you can do it. You have to find the general solution of this differential equation, and then we can find the unknown constants by using these initial conditions. After solving this, you can answer the questions which are given here in that example. You can see this example in my notes at page 40. I have already, I think, uploaded these notes. If not, I shall upload these notes after the lecture. Now, if you have any question, you can ask me. Is there a question in the chat window? जी एमन सलमान नहीं एमन सलाम.
मेरे लेक्चर से क्वेश्चन नहीं था, मुझे आपसे सिर्फ पूछना था आपके ऑफिस आवर्स कब हैं?
चले मैं आपको बताता हूँ. Is there any other question related to the lecture?
नहीं.